Alright, hello everyone, another class on ionic equilibrium today, and in this class we'll take up a very important topic called salt hydrolysis. Now, like most of the times, before we go into a particular topic, we'll want to know the need of studying that topic. And if you remember, by the end of the last class, we had seen a problem where equal amount of an acid and a base was producing a solution which was not neutral, where the pH was not equal to 7. I repeat, there was a problem where you had a given amount of acid and the same amount of a base, equal amount of H plus and OH minus. The solution was expected to be neutral with pH 7. That was not the case. So every time on mixing equal equivalents of acid and base, the pH is not equal to 7. We wonder there must be something happening in the solution which is other than neutralization, and that phenomena we are going to discuss in this class. So I'll go back to that particular problem where suppose you are given 100 ml of 0.1 molar HCl, which is say 10 millimole of the acid, 10 millimole of an acid, and 100 ml of say 0.1 molar ammonium hydroxide, which will be 10 millimole of a base. So as I said, when you have equal amount of acid and base, the two are equal, you will expect neutralization, acid base forming salt and water, and it's expected that when both are equal, 10 millimole each, both will get over. You can write the salts formed as 10 millimole, and naturally everything is happening in water, so water ka count is not required. Water is the medium, and you believe the pH should be equal to 7. Acid base completely reacting with each other, pH is equal to 7, expected neutral, and it is not neutral. So far we have believed acid base forming salt and water. We have wanted to know that neutralization is a very, very feasible reaction. Acid and base are like chemical enemies. Acid and base react completely, and naturally if the two are equal in amount, the two will neutralize completely and the solution will be neutral. Now that will happen only if both the acid and the base are strong. If both the acid and base are strong, like out here ammonium hydroxide is a weak base, but had it been HCl and NaOH, if both the acid and base are strong, then in that case equal amount of acid and base will indeed produce a neutral solution with pH is equal to 7. If either the acid or the base or both are weak. So I want to put it down. If either the acid or the base or both are weak, even on mixing equal amount of acid and base, the pH is not equal to 7. The solution is not found to be neutral, and I want people to start this topic with this note. On mixing equal equivalents of acid and base, the pH is expected to be neutral, 7. The solution is expected to be neutral. With pH is equal to 7. That will happen if both the acid and the base are strong. If either the acid or the base is weak, is weak, and means if both are weak, then pH is not equal to 7, the solution is not neutral, the solution is not completely neutral. The solution is not neutral even when acid and base are equal in equivalence. H plus and OH minus are equal. If either the acid and or the base is weak, the solution is not neutral, pH is not equal to 7, and I repeat, we start wondering that other than neutralization, something else might be happening in the solution. So far we have believed that acid and base forming neutralization is a very feasible reaction. It's a very feasible reaction. Forming salt and water, acid base forming salt and water is a very feasible reaction. When the pH is not equal to 7, we start wondering maybe a little bit of salt is reacting with water, maybe a little bit of salt is reacting with water, maybe neutralization is also reversible, maybe neutralization is also reversible, and the reverse reaction will be salt reacting with water. It will happen to a small extent, it will happen to a small extent. This is how you represent a reversible equation which is strongly driven in the forward direction. This is how you represent an equation or a reaction which is strongly driven in the forward direction, happens to a very large extent in the forward direction, just a little bit backwards. Very largely driven in the forward direction, just a little bit backwards. But even if it's a little bit backwards, it's a reversible reaction. We'll believe even neutralization is reversible. And what is the reverse of neutralization? The reverse of neutralization is salt reacting with water giving back acid and base. Salt reacting with water giving back acid and base. Something reacting with water breaking down could be called hydrolysis. So the reverse of neutralization, this forward is neutralization, this backward is salt hydrolysis. And right away we'll know that we're talking about a process which is the reverse of neutralization. We're talking about a process which is the reverse of neutralization. And if a small amount of salt reacts with water giving back the acid or base, depending which is stronger, the pH might be slightly more or less than 7. Now time now to deal with salt hydrolysis with different types of salt. I told you when it's a salt of strong acid and strong base, when both are strong, that is the only case when pH will be equal to 7. We'll talk about it at the end. When both are strong, salt hydrolysis might not be happening. But if any of the two are weak, the pH is not equal to 7 and naturally it becomes reversible. We'll begin with salt of strong acid and weak base. We'll begin with a salt of strong acid and weak base. That was there in the problem which we began with. Remember, ammonium chloride is a salt of strong acid and strong base, and it might begin with HCl ammonium hydroxide forming ammonium chloride plus water. It might begin with a neutralization where both are equal in amount. Now we are considering the reverse reaction, believing even neutralization is reversible. We are talking about the salt hydrolysis of ammonium chloride. Now suppose, first of all, it's the salt of strong acid and weak base. It's a salt of strong acid and weak base. The strong acid being HCl, the weak base being ammonium hydroxide. First of all, ammonium chloride plus water and the reaction moving back. So this is the reverse of neutralization. I want to write it in the true form. The true ionic form will be, there is nothing like ammonium chloride in water. I keep on saying, पानी में अमोनियम क्लोराइड नहीं होता है, पानी में अमोनियम और क्लोराइड होता है, पानी में अमोनियम और क्लोराइड होता है. So ammonium hydroxide is a weak base, so it will not ionize completely. HCl is a strong acid, so it will ionize completely. पानी में HCl नहीं होता है, पानी में H plus और Cl minus होता है. There is nothing like HCl in water, it's H plus and Cl minus. I keep on using this language. There is nothing like ammonium chloride in water, it's ammonium and chloride. We can cancel Cl minus on either side. When we cancel something on either side of an equation, of an equality or reversibility, जिसको कैंसिल करते हैं ना, उसका मतलब होता है उसमें कोई चेंज नहीं हो रहा है. पहले भी Cl माइनस था, अभी भी Cl माइनस है. तो इक्वालिटी या रिवर्सिबिलिटी के दोनों तरफ जब कुछ कैंसिल करते हैं, इसका मतलब है उसके अंदर में कोई चेंज नहीं आ रहा है. पहले भी Cl माइनस था, अभी भी Cl माइनस है. And when you do this, it will appear like it's a case of cationic hydrolysis. You got to learn some terms. It will appear like with salt of strong acid and strong base, it's a case of cationic hydrolysis. It's a case of cationic hydrolysis because you see the cation, giving you ammonium hydroxide and H plus. And right away one thought would be, although I know acid base forming salt and water to begin with, if some amount of salt with water gives back the acid and base, it's a cationic hydrolysis. If it's a strong acid weak base salt, cationic hydrolysis. And now I can see if this happens to a small extent backwards, strong acid weak base, H plus रहेगा, pH हो सकता है 7 से थोड़ा कम हो, solution might be slightly acidic. दोनों बराबर लेने से भी pH 7 नहीं आएगा. सॉल्ट पानी के साथ में रिएक्ट करके अगर थोड़ा सा भी पीछे जाता है, कैटायनिक हाइड्रोलिसिस ऐसे होता है, जिसको कैंसिल करते हैं मतलब उसमें कोई चेंज नहीं है. और कैटायनिक हाइड्रोलिसिस, स्ट्रॉन्ग एसिड वीक बेस, इफ इट गोज अ लिटिल बिट बैकवर्ड्स, the acid being stronger, you will see H plus in the solution. pH will not be equal to 7, it might be slightly less than 7, and the solution might be a little acidic. You will want to copy all of this at your convenience, and I am going to start with this equation. You will want to copy all of this at your convenience, and I am going to begin with this particular equation. So once you have copied it, you will know that salt hydrolysis is basically the reverse of neutralization. And now I'm going to begin with this final equation. We're going to start with this, and we're going to deal with it like we have been dealing most of the cases of ionic equilibrium. I guess I have been able to convey the name of the process, salt hydrolyzing back. Hydrolysis means breaking because of water. In this case, strong acid, H plus, the pH might be less than 7. The solution might be a little acidic. We'll go into the calculation of pH now. Because that is what we have been doing most of the times in ionic equilibrium. For a given solution, it might be a solution of ammonium chloride to begin with. In the problem, they might give you a solution of ammonium chloride to begin with. You will know that the solution of ammonium chloride is not neutral. It's slightly acidic because it's a salt of strong acid and weak base. Or they might start with equal amount of HCl and ammonium hydroxide. In both the cases, you will want to apply salt hydrolysis when the acid and base are equal. When both have got over, only salt is present, and it's a case of salt hydrolysis. Now, if suppose I go back to this ionic form, cationic hydrolysis, things we have been doing in ionic equilibrium right from the beginning. If it's C molar to begin with, and the degree of hydrolysis is small h, like alpha, which was degree of ionization. Suppose this is degree of hydrolysis, this is degree of hydrolysis. I have told you in the past, degree of ionization, degree of hydrolysis means out of 1 mole, H mole hydrolyzes. So if it is C mole, amount hydrolyzing will be CH. 1 मोल से H मोल जाता है तो C मोल से CH जाएगा. ये अगर CH जाता है तो ये CH बनेगा, ये CH बनेगा. We'll want to arrive at the CH calculation, the pH calculation out of the H plus concentration. And like Ka, Kb, this time I'll want to write KH, which will be the hydrolysis constant. Now this hydrolysis constant will be naturally, like any equilibrium constant, product upon reactant in square bracket molarity. Naturally, this could be written as CH into CH upon C1 minus H. 1C will get cancelled. Because H is very, very small compared to unity, you can take 1 minus H almost equal to 1. Like we did in Ostwald's dilution law. So 1C will get cancelled. 1 minus H is almost equal to 1, and this will look like a CH square, where 1 minus H is almost equal to 1. We had seen Ka is equal to C alpha square in the past. Now I see KH is equal to CH square. So nothing very different. And with KH is equal to CH square, I can write H is equal to root over of KH by C. So this is also kind of obeying Ostwald's dilution law. If it is more diluted, it will hydrolyze more. And all of this was to get H plus. And I could write H plus as CH, which is C into root over of KH by C, or equal to root over of KH into C. So this is how I can arrive at the H plus and pH calculation if suppose the value of KH is given to me. Now out of so many acids and bases producing so many salt, it's unwise to deal with the value of KH. Rather we'll want to deal with the value of Ka and Kb only. Now along with this equilibrium, another equilibrium, which has been playing in the same solution is ammonium hydroxide. This is another equilibrium, and this is represented by Kb. Kb is again product by reactant. This is again product by reactant. So this is something we have been knowing. This is again product by reactant. And now if you look at the ionization of this weak base, This is how Kb looks. This is how Kh looks. This is how Kb looks. This is how Kh looks. And right away, if you multiply the two, if you multiply Kb into Kh, if you multiply Kb into Kh, now Kb into Kh, you know, ammonium hydroxide will get cancelled. Ammonium will get cancelled. You will get the product of H plus OH minus, which is nothing but Kw. And now you can write for Kh as Kw upon Kb. Now just one more mathematical step and we are towards the calculation of H plus and pH. But yet again you will want to, you know, do this of your own a couple of times so that you get used to it. You are used to Ka is equal to C alpha square, Kb is equal to C alpha square. Now it's Kh is equal to Ch square, where H is the degree of hydrolysis. This looks very similar to the expression of Ostwald's dilution law. H is equal to root Kh upon C. H plus is what I want. H plus is Ch, root into Kh into C. Certainly these expressions are familiar, and I am going to replace this Kh with root Kw into C upon Kb. So this is what we need to do. We are going to replace Kh with Kw upon Kb because we will not want more constants to be learned. We have a list of Ka, Kb already. So why, you know, for different salts produce another set of Kh values, I can relate Kh with Kb using a popular constant Kw. So you will want to be comfortable with H plus is equal to root Kw into C by Kb, and then a couple of steps and we'll be able to calculate the pH of the solution. But yet again, before that, you will want to copy down everything. And as I did tell you, finally, it's likely that we'll find the solution to have a pH slightly less than 7. Once we reach this point, H plus is equal to root Kw into C by Kb, and a couple of more steps. I think this is very comprehensive. Kh into Kb, ammonium cancelling out, ammonium hydroxide cancelling out, you are left with H plus OH minus, which is Kw. We'll want to begin with the step. Now with H plus is equal to Kw into C upon Kb to the power half, taking minus log on both sides, you will get minus log of H plus is equal to minus half log Kw minus half log C, and naturally because this is in the denominator, taking minus half log on both sides, this will be plus half log Kb, and now the final step would be the calculation of the pH. So minus log of H plus will be equal to pH. Kw is 10 to the power minus 14. So log of this is minus 14, and minus half of minus 14 is 7. This is 7. Minus log Kb is Pkb. Naturally, minus log Kb is Pkb. So plus log Kb can be written as minus Pkb. So this will become minus half Pkb. Minus half log C. This is how you can calculate the pH of a given amount of ammonium chloride. This is how you can calculate the pH of a given amount of ammonium chloride. 7 minus, and in all likelihood it will be less than 7. In all likelihood this will be less than 7. This is how the pH is calculated using salt hydrolysis for a salt of strong acid and weak base. So we'll want to get started with one particular form. When it comes to the other form, which is strong base and weak acid, in that case it will be a salt like sodium acetate, which might again begin with acetic acid and NaOH in equal amount, and giving a solution which is not neutral. So if you again believe this is reversible, then CH3COO minus Na plus water, reversibility. This is salt hydrolysis, and this is when it's a strong base weak acid scenario. When it's a strong base weak acid scenario. Remember, this was for a strong acid weak base. This was for a strong acid weak base. For a strong base weak acid scenario, there is a reason why I do not dissociate the weak electrolyte, because I'll write a Ka for this, and I'm writing the reverse of it. So this will be CH3COOH. The weak one will not be dissociated, and NaOH पानी में Na plus और OH minus ही रहता है. ये cancel करोगे. For this type of salt, you will see it's anionic hydrolysis. And this time you can see OH minus out here. So this might be a pH slightly more than 7. I'll want you to try it of your own. Find the corresponding pH. Like we did for a strong acid weak base, you'll want to try this of your own. And then the third type will be when both the acid and the base are weak. I'm certainly going to record videos for all the 3 types of salt, but I wanted to give you a head start with one particular example, and I'll either want you to attempt the rest of your own, or certainly look into your textbooks, think over it before I give you the pH calculation in the upcoming videos. So this much for the time being, and I think I have been able to convey the concept of salt hydrolysis. And as expected, the pH of ammonium chloride, I repeat, which was a strong acid weak base salt, I might just write it one more time here. NH4 plus water becoming NH4OH plus H plus. You find H plus here, the expected pH is less than 7, it's expected to be acidic, 7 minus. So now you can calculate the pH of a salt like ammonium chloride. It will not be equal to pH, and what's coming to use is salt hydrolysis. Let's for the last time recall that I'm going to use these formulae, these results, only if only salt is left. Only if the acid and base are over and only salt is left. Either the acid and base are over, or they give you a problem involving equal amount of the two, so that they eventually give you salt only. With the salt left, salt hydrolysis coming into play, the pH will be slightly less or slightly more than 7. We'll talk about this kind in the next class, next video. This much for the time being. Thank you so much.